Hi everyone, and welcome to lecture 11 of the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vecev and I'm professor at ETH. So in this lecture 11, we're going to be studying combinations of logic and deep learning, which is quite an interesting combination because of these are two essentially polar opposites almost in the computer science spectrum. Logic focuses on specification, on formal meaning, on semantics, while deep learning focuses on differentiable reasoning, continuous reasoning optimization. So what we're going to see is how to actually combine these two areas of computer science in a way which allows us to solve some very interesting and fundamental questions in learning. And so we're going to be focusing in this lecture on two central questions. So the first question we're going to be studying is one of querying the network, seeing the network essentially as a database and posing questions to the network and getting answers. And so some of these questions, as we'll see, are quite important, and essentially the whole mechanism that we'll show is going to generalize this generation of adversarial examples that we looked at in earlier lectures. Another direction that we're going to be studying is one of enforcing background properties, word knowledge into the network. And so if you have some belief that some property should hold, that should be true, we're going to be studying at ways to specify that in a clean way and enforce it into the resulting machine learning model. And while we're doing this, studying these questions, we're going to be doing so in the context of particular theoretical guarantees that are desirable for these methods. Now, this lecture is almost entirely based on a paper that we published last year, DL2. So DL2 stands for Deep Learning plus Differentiable Logic. So bridging these two worlds, essentially focusing on answering these two questions that we posed, one of querying and training the neural network. All right. So before we get into the more technical bits, let's just remind ourselves of some of the examples that we studied in lecture 1, which showed various combinations of various queries and ways to enforce background priors with logic and deep learning. So for instance, one setting where this makes sense generally is in settings where deep learning makes decisions, right? So more decision making taken by machine learning models, whether it's giving out credit, job application decisions, university admissions, elections, and so on. So it's more and more critical to actually understand what these decisions are, how to influence them, right? And so let's see an example here to best illustrate this point. So we have a neural network here on the left and an applicant who has applied for a bank credit, but he was rejected by the bank. And right, so one question is that the bank analyst may have is to give feedback to the client is what do they need to change, what is the minimal changes they need to make so that the chance for a bank credit increases, right? And so one potential answer that such a system that we are going to be describing in this lecture could give is that, to increase the probability to be greater, let's say, than 84% of receiving credit, the applicant should increase their income by at least 5,000 and be employed for a little longer, right? For at least 3 more months, for instance, right? So this kind of feedback would actually be very useful to the applicant, some action for feedback. And these are the kind of questions that we actually will be able to answer using the techniques that we're seeing today. So note that we are not looking, as we did in the last lecture, into the internals of the neural network, the particular activations and neurons that are responsible for the prediction. We are studying mostly seeing the network as a database and posing questions, or training the network in a way that where you can enforce some beliefs. So let's see a few examples, perhaps some closer to the setting that we've been studying so far, which is adversarial robustness. And so here would be one example of posing a query, an adversarial robustness query. So we have a neural network on the left. We have an image of a deer. right? We may ask the engine to find an adversarial example that satisfies certain constraints. So for example, we may want that to find an image I where the image is classified to 9, which is a truck here, right? Where the image is within some distance of the original deer image. According to L infinity norm, it would be greater than 5 and less than 25, let's say. All right, so as we'll see later, in fact, adversarial example generation can be seen as just a special query in the kind of languages and logics that we're going to be looking at, right? So it's just going to be a specific query, all right? Okay, just to relate some of the examples we've seen earlier in this adversarial example generation, one of differentiating networks, like computing an input that differs the two networks. We could have a setting where we have a couple of networks, NN1 and NN2, and we have an image at the bottom, image 9. We may say, well, can you find the input I, an image I, which is classified differently by the two networks NN1 and NN2. So one classifies it as 8, one classifies it as 9, right? Such that some parts of the image 9 are kept the same in image I. So for instance, the pixels in the row 0 to 9 are kept the same, but all the other pixels can be changed as the system sees fit. So rather than tinkling around with loss functions as we did before, when we were trying to answer these questions, why not we just have a high-level language which we would be able to essentially automatically derive the loss function, right? So this would be a couple of examples that we saw before, but now somehow posed in this more general way. Okay, and of course we'll be able to pose much richer questions than the ones that we've seen so far. Now, of course, when we're looking at these examples, we see immediately that we have one part is the neural network, right? Right, the differentiable function, mostly differentiable, and all right, and then we have some other parts of the query, which are the hard logical constraints, like the O infinity norm has to be within some range, let's say. Okay, so we know that this is tricky, and we know that we need to somehow bridge these two worlds of, you know, the logical formula or the query language here contains differentiable components, it contains logical constraints, and we need to somehow bridge these two worlds. So that's what we're going to be concerning ourselves with. Beyond just querying the network and seeing it as a, you know, as a database or a set of databases, multiple networks, we may also want to enforce some word knowledge, some background priors, belief into the network. So we may have a setting where we have a network architecture, which is where the weights are not yet determined, right? As a topology, we have some labeled data set of images, right? Maybe even together with an unlabeled data set. And then we also have some logical property that we want the network to, the resulting model to satisfy, right? And so we're going to be studying at ways how to enforce these properties into the network, right? And interestingly, as we'll see, by providing this additional bias, these additional priors, right, that you may have knowledge of in the particular domain that you're training your network, right? This potentially can help you actually with increasing the standard accuracy, which is quite nice. So essentially what it says is that the additional prior or background knowledge that you provide may allow you to label fewer examples, right, than before, which can potentially solve a very fundamental problem in deep learning, which is typically quite data hungry, one of just reducing the amount of labeled data. Or if you already have a lot of labeled data, you'd be able to, you know, impose some constraints that you believe should hold, perhaps from a security perspective as well, or fairness or a bias perspective. All right, so we're going to be looking at this kind of use cases, instances of these use cases later in the lecture. Okay, so we essentially have two parts to this story. So one is the declarative part, which is the what part. What are these queries? What is this background knowledge, right? We need to express it in some way, some declarative way, hopefully, at a high level. And then we need to have the operational part, which is the how. How are we actually going to realize these queries? How are we going to realize this background knowledge incorporation? So we're always going to try to separate these two worlds so that we have clean solutions and to potentially separate the what from the how, because there could be multiple hows, multiple ways to realize the declarative specification. So let's first focus on part one, which would be in querying the neural network, right? We want to pose questions to the neural network and get answers from the neural network. So as we mentioned, first is going to be the what. We need to specify what these queries are, to specify them in some way, in some high-level declarative manner, so that it's convenient for users to pose them, right? And then we're going to study the how, right? How do we actually implement that? So first with the what. So perhaps not surprisingly, to express declarative queries, one way, one direction in which one can go, in where we're going, is in using logic, right? So logic has clear semantics, it is well understood, and it captures high-level declarative insights. All right, so we're going to use standard logic. So with no quantifiers, no universal quantification, no existential quantification. Okay, so quantifier-free logic, we're going to have the standard connectives, negation, inequality, conjunction, disjunction, strict inequality, just normal inequality, and implication. We're going to have functions from vectors to vectors, right? It could be the neural network taking an image and producing a probability distribution over the labels in this particular domain. We have the standard terms, variables, constants, which are vectors of reals, function application, like applying the neural network to an input, and the standard arithmetic expressions over terms, additions, subtraction, multiplication, and so on. Okay. Right, so this is just the basic quantifier-free logic over the reals. Okay. So now let's illustrate some points about the logic on this running example. We're going to be seeing this example throughout the lecture. I've picked it specifically because it illustrates different points. It also is kind of familiar to us from the adversarial example generation, right? So first thing we see here in this logical query, right? This query is that we have this class keyword. So this class keyword here is nowhere to be found in the actual logic. It's in fact syntactic sugar. So we need to find a way to kind of expand this a little bit and get back to our logic, all right? So if the user poses some question like this, which is convenient for them, this kind of question can be compiled down or directly translated into the logic. And what it does is what you would expect. It says that, you want the class to be 9, essentially true. So you can encode that in the logic directly as saying that the probability for all the other labels other than truck, right? Let's say K is 10, we have 10 labels. So from 1 to K, 1 to 10, the probability for all the other labels like label 1, label 2, and so on. So J would be, let's say, label 1, 2, 3, 4, all the way to 10, except 9, because 9 is the one we care about. The probability that the image I is classified to any of these labels is less than the probability that it is classified to truck, right? So this is one way to enforce it, and there's a conjunction of these constraints, right? And this expression now that we get, the entire expression, is something that we can express in our logic. We don't have this class syntactic sugar anymore, so we can just directly use this constraint, okay? And the only thing we have in this logical formula here, we have these constants, dr, 5, 25, 9, and so on. And we also have the function application, which is the nn, and we have importantly, we have the free variable I, because I is the one that we're trying to find the satisfying assignment of this formula. Right, and this is what I just said. I wrote it on the slide just in case, so we have it in written form. We have two functions, nn and the L infinity function, which computes the L infinity norm. Right, we have a bunch of function applications, and we have a bunch of constants, normal constants, vectors, right, of reals, and we have one free variable. And our goal is to find the satisfying assignment to the formula, to find the value for I here. Okay, so that's just as a high-level point. You see that you can have a declarative language involving the class keyword and just compile down to this lower level logic, right? Just like you deal with SQL, you may have a high-level language and compile down to relational algebra, let's say, for instance, or some other representation. Okay, so now we're given this formula in our logic, right? So the most natural, the problem that we want to solve is we want to find the satisfying assignment for the free variables in the formula. So in our case, this is the image I. Okay, we need to find some instantiation for the pixels of I, which solve the formula. Okay. So if you see it that way, the most natural question would be, well, there's a lot of work on satisfiability, right? But of course, not with standard SAT solvers, which are over the Booleans, but with generalization of the SAT solvers to something called SMT solvers, which are satisfiability modulo theory. So for instance, the Z-free solver or the ISIS SMT solver, which have been very successful in problem verification tasks. But the problem here is that, so theoretically, you could just give this formula to the SMT solver to find I, right? Some assignment to I that makes the formula satisfiable. The problem here is, however, that SMT solvers are typically not dealing well. They don't work well with nonlinear arithmetic. And in the neural network, we have quite some nonlinear arithmetic with all the activations going on, put together in different ways across different layers, right? And we could have multiple networks in our formula. So if you try this SMT-based approach, just feed the formulas and ask it to find a satisfying assignment, then it's really not going to do much. It's going to time out unless the networks are really, really small. And so this approach doesn't really work. So we need another approach, okay? And so now what we're getting into is not just the what, right? What is the query, which is expressed in that logic. We're getting into how do you actually answer those queries, right? Involving neural networks, right? And so the key insight here is that rather than just calling a standard SMT solver, the idea is to essentially reduce the problem to an optimization problem, okay? Reduce satisfiability to optimization. And this is not the first time we've seen connection to optimization in this course. Remember earlier when we looked at complete certification, we saw a connection with where we could pose the complete verification problem as an optimization problem and solve it using mixed integer linear programming. And a similar kind of situation arises here, except we're not interested in verification, we're just interested in solving the satisfiability problem. So we're going to find a way to essentially translate this formula into some loss function, some differentiable loss function, and then apply more or less standard optimization in order to find a satisfying assignment for I in this case, okay? And then what we're going to see now, we're going to see what is the desired property of this translation, the mathematical property, okay? And then we're going to see a particular translation, okay? And that particular translation, we're going to see this T is going to satisfy this mathematical property, but potentially there could be other translations as well that satisfy this property. We just found this particular translation to be quite instructive for this work and instructive for the lecture and also quite clean. But that doesn't mean that there is not other ways to define this translation. Okay, so first on the mathematical specification, the theorem that we would like to have here before we talk about this translation. What theorem would like this potential translation from logic to loss to satisfy? So here's the theorem. What we would like to have is a situation where if we find the values where the function is 0, right? In values x where the function is 0, then these values are a satisfying assignment to the formula phi. And if there is a satisfying assignment to the formula phi, then that satisfying assignment to the formula phi, when plugged into the translated loss, right, T of phi, actually also is 0. So this is an if and only if theorem, right? So if you can happen to find a solution with your optimization problem where the function is 0, that's great, because then you know that this is a satisfying assignment, and vice versa, you know that all satisfying assignments make the function 0. Okay, so that's the key property of the translation. So it's not just some random translation that generates some random optimization problem. There is some mathematical rigor to this translation. Okay, as I mentioned, the goal given this theorem is essentially to find an assignment to find values to where the function is 0, and we know that this would be a satisfying assignment. Okay, of course there could be many satisfying assignments, and then thus many potential values where the function is 0. So now let's look at the translation. So now that this is a little bit on the house side, this is a particular translation, right, that satisfies this theorem, right? But there could be potentially other translations as well, okay, that also satisfy the theorem. So now let's look at this translation. This is the whole translation is summarized in one slide. And what we see here is several points. So the translation of the last 4 terms is largely recursive, right? It's defined recursively in terms of other terms. Okay, and only in the first 2 terms, inequality and less than recall, are these defined as without the recursive translation. So take a look at that. Another point here is that the resulting loss function here that we have, right, that we obtain with this translation is non-negative, and this is because the max here is gives you 0 or some value greater than 0. Okay, so that is non-negative, and the indicator function t1 equal to t2 and the brackets around it, this is the indicator function. It's either 0 or 1, so this is also non-negative, and then we have addition and multiplication, so it's easy to see that this is a non-negative loss function here. Okay, so now let's take a look at this translation a little bit to see what it is and get a little bit of an intuition. Okay, so what we have here in the first term is we have the term t1 less than or equal to t2, and we translate this with the max here, right? And so what we see here, just to get a bit of an intuition, if t1 is less than or equal to t2, if we pick some value where t1 is less than or equal to t2, then t1 minus t2 is going to be a negative number, right? And then the max of 0 and the negative number is going to give you 0. And so the formula is satisfied and the loss is 0, which is what we want. Okay. Now let's see if the t1 is actually greater than t2. So the formula is violated. What would happen then? Well, then the max is essentially going to be the max of 0 and the size of this violation. So the greater the distance is between t1 and t2, the greater t1 is greater than t2, the more the violation will be. So essentially the magnitude of the difference captures the how much greater t1 is than t2 captures the violation of the loss, the magnitude of the violation, right? So this kind of gives you a little bit of an intuition here, and obviously the closer the values are, if t1 is greater than t2 by just a little bit, the violation gets smaller and you get closer and closer to 0, which is great, which is what we want in practice. Okay. Now the other translation is that doesn't require recursion, is the inequality between two terms, t1 not equal to t2, and this is translated to the indicator function of t1 equal to t2. So the indicator is going to be 1 only when t1 is equal to t2. So 1 means it's away from the 0, and so right, it's not satisfying assignment to the formula by any means, right? And for any other values where t1 is not t2, right? So the formula is satisfiable, then the indicator is going to be 0, indicating that the formula is satisfiable, which is what we want. Now, one point here that I'd like to make is about optimization, right? So the gradient of this indicator is always 0. And so what this essentially means is that when you do optimization with this resulting loss function, which involves these terms here on the right, these indicators, well, if you're at a situation where T1 is T2, T1 and T2 are equal, so let's say T1 is free and T2 is free, some values, right? They value to that. Okay, then because the gradient is 0, there is no way for the optimizer to actually move away from this. So you end up at 0, and that's not great because we want to find values where the formula is satisfied and the indicator is 0. And so in that case, what you're actually hoping to happen is for the remaining terms in the formula, whatever other terms are in the formula, are changing the underlying values, right? And so they're leading to change in the satisfying assignment. Their gradient is not 0. And so changes are happening due to them, and hence shifting away from this specific point where T1 is equal to T2. Okay, so just a point here. Okay, so the rest of the translation is fairly standard as you expect. So the term T1 equal to T2 is the same as T1 less than or equal to T2, and T2 is less than or equal to T1, and you translate the resulting expression, right, to get your loss. And if you do that, you would end up with the absolute value of T1 minus T2. Again, non-negative function satisfying our theorem. Okay. So this translation is recursive. T1 less than T2. Again, just the basic rules of logic. You can rewrite it with the T1 less than or equal to T2 and T1 not equal to T2. And we just saw already how to translate those. Okay, so when we code the T, it will just translate it in the way that we saw before. Okay, and the conjunction we haven't looked at yet. The conjunction gets translated to a plus. We'll see it in a second. And so you'd end up with the following translation here on the bottom. Okay, so this translation is also quite direct, I would say. Now, as far as disjunction goes, we need to see disjunction and conjunction. So as far as disjunction goes, disjunction gets translated to multiplication. And so disjunction, or between two formulas, when is the resulting formula satisfied? Well, the resulting formula is satisfied when you found a satisfying assignment, which makes one of the formulas satisfied. And whether the other is satisfied, it doesn't really matter, right? As long as one of them is satisfied. Of course, if both are satisfied, that's good, but it's enough for one of them to be satisfied. And this is what this translation says. So if one of them is satisfied, then translation of that formula evaluated at that satisfying assignment is just going to give you 0, right? Okay, and if that's the case, then the whole translation, the multiplication by 0 is going to give you 0, and thus the whole thing is 0, which reflects that having even one of the terms being satisfiable is enough for the resulting loss to be 0 and for the formula to be satisfiable. Okay, and so right, if both are not satisfiable, right, if both of these are not satisfiable, then the T phi, translating phi and then translating psi, are going to be non-zero, and when you multiply them, you're going to get some even larger value, which is non-zero, and you're going to try to reduce this value as much as possible, right? Okay, hope this gives you some intuition. And then for the conjunction, it's a plus and not multiplication, because this reflects the fact that both of these formulas have to be satisfiable with the same satisfying assignment, of course, for the resulting translation to be 0. And so only when both are satisfied, find a satisfying assignment where both are satisfiable. So then the resulting translation of these formulas is going to be 0. And only then when you add 0 plus 0, you're going to get 0. And so multiplication doesn't work here. It has to be addition, right? And if one of them is not satisfied, right, if one of these guys is not satisfied, then, and the other one is satisfied, well, that's a problem. Then the resulting loss is not going to be 0. Okay, and you can check that. And so this is a translation. Hope it gives you a bit of intuition why it is the way it is. And you can yourself check that the translation actually satisfies the theorem that we posted on the few slides ago. All right. Now let me give you a quick example just so that you get a visual understanding of what goes on here. So on two kinds of formulas, one is one that has satisfying assignment, one that doesn't have satisfying assignment. So if you look at the one that does have satisfying assignments, for instance, the logical formula x greater or equal to 2 and x less than or equal to 5, okay, if we translate it using our translation, we'll end up with the expression on the right, the max 0 and 2 minus x plus max 0 x minus 5. Okay, and if we plot this function here, we see that the function is 0 when x is between 2 and 5 inclusive, right? Which is exactly where the formula is satisfiable. It's an if and only if situation here, all right? Now, if you look at the case where the formula is unsatisfiable, like x is greater or equal to 4 and it is less than or equal to 3, which is not satisfiable clearly, then you see that this function is strictly positive, right? The function is never zero. So you just cannot find a satisfying assignment here using optimization because it just doesn't exist. All right, so this gives you a bit of intuition. Now we can look at a bit more complex constraints closer to the ones that arise in practice, just to give you a even more visual intuition. So you can look at these 8 constraints on your right. These are octagonal constraints, 2 variables per inequality, as you can see here, x minus y less than or equal to 3. So these are some kind of restricted polyhedra constraints, right? And you can plot the lines. So each of the line here, like the red lines, the blue, and so on, correspond to these constraints, right? You can draw them yourself. And I have done that just so that to illustrate this point for you. And in two dimensions, these equalities can produce octagons. That's why it's called octagonal constraints. Okay, so we have 2 dimensions, x and y. And when you plot them like this, you would end up with some region intersected by all the lines, which is an octagon where the formula is satisfiable. So for these values of x and y, the formula is satisfiable. Now, if you take that formula up top on your top right and you translate it down to a loss function using the translation t that we saw before, okay, you're going to end up with some mathematical loss. And if you plot that loss on your right here, you see that this loss is 0 exactly in the values where the formula is satisfiable. So for x between the values 1 and 7, and for y between the values of 2 and 8. So this kind of gives you a nice, just draw the correspondence here. This gives you a nice visual understanding. And you can yourself play with different formulas and run the translation, get a mathematical function, and just plot it in and see what you get. It's quite nice to get an intuition. So I hope that gives you a bit of a good visual intuition what is going on. Okay, so we saw this logic, we saw the translation, we saw that we can have high-level language that translates to the logic. We have the theorem that the translation from logic to loss satisfies, right? So now let's get back to our, more realistic constraints, right? So this was the running example that we're using so far, okay? And that was the original formula up there. You can unfold it like this: the conjunction, the big conjunction, into all of the conjunction on the left, and you could translate it, right? And you would end up for each of these terms, for each of these conjuncts, if you translate them, you would end up with a term in the loss functions on the right, as I'm connecting them here now. All right, so it would get you wouldn't expect a user to start sitting here and start writing a lot of these constraints, right? Or even something more complex. Imagine for some bigger queries involving multiple networks and so on, how long this can become. It's much nicer to actually have our class keyword and just have the logic to just define it directly instead of writing this stuff by hand like this on the right. That's one really nice advantage of usability that and it's, of course, a lot more intuitive and easier for non-experts who don't care about loss functions to just impose and ask queries of the neural network. Okay, so I hope this gives you a bit of an idea. Now, when you actually concern yourself with the how, beyond just the translation, right? Given these formulas at the end, you need to actually solve them in somehow. Like you have a loss function and you're going to have some optimizer that is going to try and minimize that loss function, because we know that at 0 are the satisfying assignments, right? But the problem is that in these logical formulas, and of course in the high-level language, in the queries that produce these logical formulas, like the syntactic sugar on top of the logical formulas, on top of the logical fragment, it could have constraints like these box constraints here, like I is in 0, 1, which we know are difficult to optimize with standard gradient-based methods. We know this from our study in adversarial example generation. And we know that we need to do something about this, right? If we just leave it in the formula, it just may be difficult to find a solution. So what typically happens here in practice is that you take out those constraints from the formula and from the high-level query, and then you translate the query, your logical formula into the loss without those constraints. And then you take those constraints and put them as part of the optimizer, like BFGSB, where B stands for box constraints, just like we did before, except that now it's a richer setting due to this translation of the logical formula into the loss, right? Okay, so let's just see the end-to-end flow here, what we have. And so what we are seeing here is that we have our original formula phi. Okay, this could have been produced by some high-level query, but at the end we end up with some logical formula phi, just like we had on the previous example with our running example, quantifier field in some quantifier field logical fragment. We translate this logical formula using our translation T into a loss. So we translate it like this, okay? And then once we translate it, and again, as we mentioned, some parts of the logical formula can be translated, and other parts, these box constraints, for example, we can take them out, completely out of the translation, and pass them later to the optimizer. So these two, the loss and the box constraints, right? We can handle them with a particular optimizer that we use. In this case, the LBFGSB or some other optimizer, right? And end up with a solution, hopefully at some I, some assignment to I, hopefully something that is makes the loss 0. So let me just put some dots here just in case. Maybe I put 3 dots because this is still a 9, just to differentiate it from the original image over here. This 9 and this 9 are different because 9 is the input one, and we are finding variants of this input 9. These variants may be just adding a bit of noise to it that the optimizer does. Subject to the constraints, remember that it has to be within some distance of the constant 9 here that we're passing. Okay, so you can think of this pipeline here as a generalized adversarial example finding, right? Generalized finding essentially points, inputs that satisfy a given property. In that case, with adversarial robustness, it was finding inputs that that violate the robustness property. Here we are trying to find. Here we are generalizing this because we are not just we are also looking at translation of a potentially much richer fragment of logical property than just robustness. Okay, so we're trying to find a point that satisfies the logical formula. In the particular case of robustness, it would be finding a satisfying assignment that essentially is violating the robustness property, okay? Or satisfies the negation of robustness if you want to be seeing on the other direction. But ultimately, this translation from logic to loss really generalizes this idea of finding points that satisfy a formula. Okay. So this gives you some idea on the how would you implement the querying with the whole pipeline essentially end to end. Okay. And one note here before we wrap up. So this LBFGSB is tends to be slower than the PGD, right? So, but in query time, when you're doing queries, it's actually fine to use it because we pose the one query as opposed to potentially many internal queries that you do during training, where LBFGSB would be slow. As we'll see later, there would more rather use PGD, projected gradient descent, than LBFGSB. But for querying, this is fine. You can use LBFGSB. But you can also use PGD as well. Okay, so I hope this gives you a little bit of an intuition here, how the end-to-end pipeline works. Let me just clean this here so that we don't have this. All right. So now in part 2, what I'd like to do is again use this translation, just like we saw before, translation into a loss. So many of the components will stay the same. However, we want to answer this fundamental question. If I have some background knowledge, some background prior, some word knowledge about the world, how do I actually enforce this word knowledge, right? How do I do this? You can see it from a security perspective, if you like, as ensuring some security property or increasing the reliability and the safety of the network, or you want to defend the network against certain attacks, which you can specify in the manner that we are discussing. Okay, so we'll see essentially how to generalize this adversarial training methods for robustness to much richer declarative logical specs. Right, so as I said, this is going to be about incorporating background priors and background knowledge into the network, which can be seen as generalized adversarial training beyond robustness. Okay, this is the picture from before, earlier in the lecture. Just a couple of points here. That will still use the same logic as before, so nothing changes. We'll use the same translation as before, all right? Just like before, we'll be generating the loss, okay? Well, the difference here is that we need to actually define our optimization problem, right? Okay. Now, before we define the optimization problem that we're going to use to enforce the background priors, let me give you like a few scenarios here that may give you a bit of intuition of how would you actually use this. Some examples of background priors and how would you use it. And people have come up with many different ones, but these are, I've picked some that are a little bit closer to the data sets and the properties that we looked at so far in the course. So let's look at two settings of learning, like the two popular settings. One is the fully supervised setting, and one is the semi-supervised setting. So in the fully supervised setting, we're given the data set, we're given all the labels, okay? And so we have that situation. So let's see, for example, one particular query that may be interesting. So let's say the following query. All of the images in the data set that are the following property that we want to enforce. So it could be that, let's take all of the images in our data set that are classified as car, they're labeled as car, okay? We would like them to have a higher probability. We want them to have higher probability for the network to have higher probability for the label truck than the label dog, right? And so you would specify this as follows. You would say y equal to car if the label of the sample x is car, okay, then I want the probability that of this label being truck, okay, to be greater than the probability of this label being dog by some margin delta here, right? By some margin delta over here. Oh, let's see, where is the okay, by some margin delta, okay? So not just to be greater, but to be greater by some margin. Okay, why would you may want such a thing? Well, imagine in practice you have some machine perception system, and you know, it is labeling whatever it sees on the road, and you know, if it makes a misclassification potentially of a car, you'd much more likely would like this misclassification to be a truck rather than misclassification to be a dog, okay? And so you may specify such a constraint, right, to kind of ensure some kind of a some safety margin, if you like, or to be more sure that even if misclassification happens, it's not as bad as just a completely different thing with different purpose essentially. Now you can a bit generalize this constraint by saying that you don't just want this to hold for the input x for a point x, but you want this to hold for any point which is within some distance of x, right? For instance, some L infinity distance of x. So you want to hold that for all the points z that are within some distance of x. It is the case that if the label is car, okay, of this point, then the neural network again would classify this. The probability that it classifies it as a truck is higher than the probability it classifies it as dog by some margin. So this is kind of a nice safety property that you may want to enforce in your network that is desirable and it looks reasonable, right? So interestingly, if you actually incorporate these constraints during training, what you see is that the accuracy tends to reduce slightly because you have these, these constraints. And we know that in general, if you pose additional requirements, sometimes the accuracy may go down, but it could also go up, as we'll see in the next slides. But the constrained accuracy, the number of essentially points that images that satisfy this constraint, with this neural network that we train, increases by about 10%, which is quite significant. So you manage to enforce the background priors, right? To some degree, at least. There are many ways in which, many reasons why, you may not be able to achieve full satisfaction. For instance, some of the images are not even meant to satisfy this, or you didn't run the whole learning all the way to the end. You ran it up to somewhere, right? Some point, and so on and so forth. But this gives you a little bit of an intuition how you do that in the fully supervised setting. So consider the semi-supervised setting where we have a data set, but only part of the data set is labeled, and a large part of the data set may not be labeled, right? And so what happens here is, how would you actually benefit from this unlabeled data set? You don't have labels there. So one way to benefit is to provide some constraints that those unlabeled examples should satisfy, right? Okay. And of course, we know the problems of giving fully labeled large data sets. It actually can be quite time consuming, error prone, and so on. So why not benefit from this idea of providing background priors and beliefs in making use of this unlabeled data set, right? So here is an example of something that one can do. If you imagine that you have the CIFAR 100 dataset, which is essentially a dataset with 10 higher level labels, where each high level label has a 10 sub-level, lower level labels. Okay, so total 100 of labels. So we could write something like this. We can say, I want to be confident in my predictions of when I make high level predictions of the high level labels. So when I make a prediction, for instance, about people, something is, the input is a person, then I want that probability to be either very small, okay, so I'm very, very low, or it can be very high. So so I want to know, I don't want to have predictions kind of in the middle. I want to say, oh, look, I really don't think this is a person, or I really think this is a person. And same thing with other high-level labels like insects, for instance. Okay? And so the probability of a group kind of labels, right? We can specify it as we can specify it as follows. Like, for instance, the probability of the people would be the neural network classifying the input X as, you'd sum up all of the 10 labels, the sub-labels of people over here, boy, girl, baby, and so on, and you'd get your probability that something is classified as a person. So you may want to write such kind of constraints, right, that involve the both data sets or just the red data set. So in one approach, you'd completely ignore the red data set, just work with the green data set, but in the smarter approach, in approach 2, you'd actually benefit from the constraints and the that you want to enforce. And so what happens here if you actually implement this, and which we did, it's interesting that the constraint accuracy goes up massively, like by high number, like 26%, and even the test accuracy increases on the test set, which is quite nice, right? Even though we had a lot of unlabeled data here, 80% of the data was unlabeled. So it shows that these background priors, these logical constraints, can actually help you, and potentially could be a path to having a reduced need for data labeling, which is a major problem. Or if you still have lots of ways to label data, they give you a way to enforce properties, potentially security properties that you may believe should hold in the network. Okay? On that theme, let me show you another example just to tie it down to adversarial robustness a little bit more. So there was recent work last year by a couple of groups, one at Stanford and one at DeepMind, where they used this kind of idea of providing constraints involving the unlabeled data to benefit adversarial robustness and natural accuracy. And so it's really a special case of the kind of properties that we're able to express here, but it's still quite instructive, I feel, as a good example. So the idea here is that you'd have a label data set just like before, and you train your classifier on the label data set, the green data set, and then you'd use that classifier to make predictions of labels on the red data set. And what you can do after this is you can just take the union of these two data sets with the initial labels and with these induced labels, like the pseudo labels, and then you could train them adversarially using standard adversarial training. Okay, and so by leveraging in this way the unlabeled data set, by providing this additional constraint of robustness, right? Now involving the unlabeled data set with the pseudo labels, okay, you could actually improve the standard accuracy in non-trivial ways. So it improved by 5% over traits, which itself was a slight improvement over PGD, more or less as exactly as PGD, but maybe a little bit of an improvement. Traits is. But this method improved it by 5%, and the adversarial robustness also improved. So both natural accuracy and adversarial accuracy improve, showing that this kind of idea of giving incorporating specifications on the unlabeled data is actually it's a good way to pursue and to investigate more. Now let's take a look at the problem statement, which allows us to enforce background priors and these formulas that we looked at so far. Okay, so let me explain this a little bit. All right. So what we have is we are trying to find parameters, weights of the network theta, which maximize this function rho of theta. And what is rho of theta? Well, rho of theta, what it says here is we are trying to maximize the expected value of the property holding, right? So if we imagine here that we have some, we have the distribution D, or some data set which approximates the distribution, and we take a sample from this distribution, then what we're saying is that for that sample, we want the formula to hold for OZ. So for all of the free variables that it has here, right, that it has, now we bound these free variables. So for all of the Z, the formula holds. So if it has any kind of free variables, like we saw before with the I, which we were trying to find in the case of querying, we are trying for the formula to hold for all of these possible instantiations of the free variables for the given S here, right? And so either this formula is going to hold or it's not going to hold, right? It may be that there are some violations, there are some Z's for which this formula here doesn't hold. So this formula here is either going to be false, either going to be 0, okay, if it doesn't hold for the particular S, or it is going to be 1, and then it is going to hold. And we're trying to find theta, which maximizes how much this formula holds, essentially, okay? And so this is the high-level problem statement. Now, one point that we see here is we see that we have this universal quantification here, which in general is tricky to deal with. For every S, essentially, we would need to be solving this quantified problem. So one possible step to get rid of the quantifiers is to rewrite the problem a little bit into an equivalent problem, when instead of talking about the universal quantification, we are talking about a negation of the formula, right? So instead of trying to find parameters theta, which try to increase how much the formula holds, okay, we will want to find parameters theta, which minimize how much the violation of the formula holds. So let's see how this happens next, all right? So first we'll do a little bit of a rewrite here. And this is the key step really here, right? This is the step which, let me highlight this here. So we did a rewrite here. So what did we do? We did first, we rewrote the maximization into this minimization, right? And second, we got rid of the universal quantifier and we rewrote it with this expression over here with the max and the negation of the formula. Okay, so what does this really say here? Well, it's exactly what I said already. It says that we are trying to make this, we're trying to minimize how much this, how much this violation of the formula happens, right? So what this thing is doing here is it says, again, we can pick some S, some sample, and then what it's trying to find, what max Z really says is it says, let's try to find a satisfying assignment Z to the negation of the formula, okay? And so if we succeed with that, then that expression is going to be 1, okay? So the formula becomes true. And if we don't succeed, then it's going to be 0. All right, and so if we are able to find such a Z that makes this formula not phi true, okay, then that Z would also make the phi, so not the not phi, but the phi formula false. So we have found a counterexample here, right? And so we are trying to minimize, find theta, which minimize how much these counterexamples to the original formula that we saw to phi happen. And the way to do this is to just minimize how often we can find the satisfying assignment to the negation of the formula. It's just a simple logical rewrite here, okay? So the max shouldn't confuse you. This is just trying to find the satisfying assignment to the not phi formula, all right? So that's essentially what happens here. So there are 2 steps. Step 1, change maximization to minimization. And step 2, get rid of the quantifier by just trying to find counterexamples to the formula. And to find a counterexample, you find the satisfying assignment to the negation. So you find an assignment Z, which makes the negated formula hold, okay? And that's basically what happens. And you can see here, now that we're dealing with these formulas phi essentially, and if you remember the optimization problem for adversarial training, for adversarial defenses, you would remember that, you can, if you don't remember, just go back to those lectures. You would remember that again, we had a minimization of theta. That part is exactly the same as before, but this part here was more restricted in the case of adversarial training, where we were just looking at Z, right, which are in the neighborhood of S. So we're trying to find some adversarial example in the neighborhood of S, which maximize the loss, right? So we're only dealing with the loss here. We're dealing with this more general formulas phi, okay? So this scheme here essentially generalizes the adversarial training as you've seen it beyond robustness to arbitrary logical formulas. So that's one way to think about this. Okay, but one issue that we see here, right, is that we are still dealing with these hard logical constraints phi, which are either true or not, and this is not a good setup for optimization. And so expectedly what we'll do now is we will get rid of the phi by translating the not phi essentially into a loss using our translation. So this step is just the next step that we'll see is just going to be the translation that we saw before. So let's see that. Okay. So, see what happens. So let me highlight this here. So what happened here, I have splitted just the problem so that it is even easier to see the 2 optimization problems. So this part stayed the same. Okay, this part here stays the same. Now, what happened here was that we translated the formula not phi using our translation T, okay? And then what we're trying to find is a violation of not phi. If you remember, right, in the previous slide, we're trying to find assignments, satisfying assignments, which make the formula not phi hold. And if we find such a satisfying assignment Z, then this is going to make that formula not phi, is going to make it into true, into 1. But if it makes it into true, it would mean that because of our translation and the properties of the translation, it would mean that the loss at that point, at that Z, is going to be 0 because the not phi is satisfied. Okay, so if you find an assignment where Z, where the formula not phi is satisfied, then the corresponding loss that you get from translating not phi with our T is going to be 0. And so we have the problem here. What we're trying to do is when we're trying to find a satisfying assignment for not phi, it's equivalent to trying to find a value of the loss here, right, of the translated loss, which is 0. So we are trying to maximize trying to find Z that maximizes that's satisfying assignment that essentially makes not phi true, right, in the previous slide. And here, because if it is true that t of not phi becomes 0, we are trying to find an assignment here, z, okay, which makes the t of not phi as small as possible. So hopefully 0 gets it close to 0. But if not, we are trying to find the one that's as close as possible to the 0, right? Remember the t of not phi is a non-negative function, so we are trying to find that's as close as possible to the 0, and that's what would happen. And as close as possible as it is to the 0, the closer it is to making the formula not phi satisfiable, right? We already discussed this before. So this is an expected rewrite here. It shouldn't be it's just plugging in the translation and just using the properties of that translation to have the argmin here, okay? Now, once you find such an assignment here, z worst, which tries to minimize this loss, or conversely maximize the try to get closer to not phi being satisfiable, then we want to plug that z worst assignment into the original translation over here. So what this says over here is that we are taking this z worst assignment, right? And then we are trying to find what is the maximum violation of the original formula that it causes, right? So if it is as close as possible to 0 in the t of not phi, okay, then it's going to be behaving adversarially. Essentially, it's going to increase the size of the it's going to increase the size the value here of this t of phi, which is the original formula, right? And so you would get the smaller you're trying to minimize this z worst, the higher right, the higher this value here t of phi of z worst as theta will be, because this is the original formula. This is the loss corresponding to the original formula. So you're getting it further and further away from it being satisfiable, okay, t of phi, which is kind of the adversarial behavior, if you want, with respect to the formula phi, the original formula phi. So this will get you a large value as large as possible, so as bigger valuation as possible, violation as possible, and we are trying to minimize this violation. So hopefully this is clear to you why we are doing argmin here, because of the properties of the translation, and then why we are plugging in the z worst here into the original formula, because we are trying to maximize the violation here in score of the original formula. Okay. So this is the essentially the generalized adversarial training, now dealing directly with the loss functions, as we had seen it before when we tried to maximize the loss when we discussed PGD training. Okay, so I hope that this is clear. Now, several points about this solving this resulting optimization problem. Well, in practice, standard optimizers would have to solve this inner minimization problem here, this argmin. The problem is that this z that we see here, let me just highlight it just in case, this z, okay, is completely free. It doesn't have any restriction what it can range over. And this can be very hard for optimizers to find such a z, makes the optimization problem difficult to solve. And so in practice, what we do, we typically restrict this z to be in some range. So typically in some range that is perhaps some convex set around S, or just a general convex set that it can belong to. So just a slight restriction, just essentially giving the domain of Z is all we ask for here in practice. Okay. All right. So this is exactly what I say here, that typically we restrict what Z can range over, which still makes it a pretty challenging optimization problem, as we'll see, because even if Z has to belong to some convex set, projections onto these convex sets, arbitrary convex sets, is hard. We only know how to project to certain convex sets efficiently. Okay, so just a couple of points for practical when you use this formulation in practice. Just be wary where the Z belongs, what set it belongs to. Okay, now let me give you an example of how this would how would reach this minimization problem end to end here. Okay, just to get even a little bit more intuition. Let me just use the annotation. So what we have is we have some formula phi which we are interested in enforcing, as we saw before. Okay, so we want to enforce this constraint, this belief here. Okay, so it just says that if you have some constant x, okay, then what you want to enforce is for all of the z's which belong to this convex set here. Okay, so they're within some distance of x, okay, some epsilon distance of x. We want it to be the case that the neural network classifies this point z, okay, classifies this point z. So the probability that this point z gets classified by the neural network as free, let's say, is greater than delta. So this is some constraint that we may want to enforce. And we know that to enforce this constraint, we already discussed this, that we would negate this formula here in order to find counterexamples to phi, okay, to find some z's where this phi doesn't hold. And the way that we do that is by taking the negation of phi and trying to find satisfying assignments to that. Okay, so that's one step in our process. Okay, that's how we reach the inner minimization problem. Okay, so we are given this here. And then the first thing we do is we do a rewrite. So remember that in our logic, we had this implication here. We had it in the logic, but we never discussed how to translate this implication using our logic to loss translation. And so we actually treat this implication as a syntactic sugar, essentially, by just expanding into the standard logical rewrite, which is not of the first term, disjuncted with the second term. So we don't really have to define a translation for implication because we know how to handle negation and disjunction here. So this is just a syntactic rewrite here. Okay, just expanding the meaning of implication. Okay, the next part, however, is this is the semantic preserving part, this first step. But the second part is not, because we are negating the formula, and this is because we are trying to find a counterexample to the original formula phi. We're trying to find assignment z which make the formula phi not hold. And so this is the same as trying to find, as I said, assignments z which make the negated formula phi hold, satisfiable. So we do this step with the negation, just like we saw in the previous slide. Okay, so we negate the formula, and if we negate it, we again have this logical rewrite here. And so this negation it disappears here. The disjunction becomes a conjunction, and here the greater than becomes less than or equal. This is just a standard logical rewrite. Okay, so then we would end up with this negated formula, and we would be taking the final step before trying to find counterexamples. This was the translation to loss. So we would apply our translation T here to this negated phi, and try to minimize that resulting loss function then. Okay. So this is just the standard translation, right? The first term is rewritten like this, and the second term written like this, and conjunction is rewritten as addition, right? And so this is the standard rewrite we already looked at. And so then we end up with the following formula over here. And then we're trying to do argmin on this loss. We're trying to find values of z. So this x here would be some constant. So in the optimization problem before, this x here would be the s that we sampled from the data set. Okay, here's just some image x. And we're trying to find values of z which minimize this loss. And if we minimize this loss, then we'll get closer to finding a satisfying assignment to this negated formula not phi. And if we get closer to finding a satisfying assignment to the negated formula not phi, we would get closer to finding a satisfying assignment that makes the formula true of the original formula phi. Okay, so not surprisingly, such kind of problems can be difficult to solve. And let's discuss this a little bit, right? We already saw this before in the earlier lectures, but okay, so this is our optimization problem that we reach, our inner optimization problem here that we obtain. Now, what you see with this part here is really just the, this is just the trying to restrict Z to be in the L infinity bow around X of size epsilon. We know that such kind of terms are difficult to, we already discussed this before, to optimize with the gradient-based method because the gradient is very sparse, okay? And so ideally we want to get rid of them, get them out of the loss here, and we'll be left with a smaller loss and plug those additional terms somehow separately in the projected, give it to the projected gradient descent, okay? And so what we'll do is we'll keep this gray part here in our optimization problem, but we will get rid of this blue part and just take it out of the optimization problem. So our resulting argmin optimization problem just becomes this. And this additional constraint that you need to be inside the bow is passed in separately. We deal with it separately via projections, okay? So one thing you can see here why this rewrite is valid is if we're able to solve this problem here, this argmin Z, we find some assignment Z which minimizes the loss, minimizes this max over here, which is inside the L infinity bow, which is inside because that's our restriction, okay? Then if we are inside the L infinity bow, then this term over here, okay, this term over here is going to be zero, okay? Because this term over here is going to be negative, okay? This part here is going to be negative, and so the entire max zero of that expression is going to be zero. And so it will amount to just solving, so this term is not going to contribute anything to the resulting optimization problem, okay? So this is a valid rewrite here. So if you find the solution, optimal solution in the bottom problem, this would be an optimum solution to the top problem as well, okay? So so this is a valid rewrite here. So if you find solution to the bottom, optimal solution here Z, it would be a optimal solution to the top problem as well. Okay, so already discussed this many times that projections onto convex sets like this L infinity bows can be difficult. Now L infinity bows are not difficult, but there could be a more complex constraints here that you may want to project to. So projection is an important problem when it comes to this enforcing background priors or generalized adversarial training. So better projections help. Okay, so for instance, just to tie it back to when we looked at the layer-wise adversarial training in earlier lectures, the code training, there, remember, we had to project onto these zonotops, okay, we had to project onto the zonotops, and this amounted to projecting on boxes, okay, so we were lucky in that sense. So these projections kind of appear in multiple places here in enforcing the background priors, they appear also in the querying, which we solved with this LBFGSB with the box. If we have box constraints, they appear in the standard adversarial training and adversarial example finding. So projections are very important, right? Okay, so this gives you a little bit of an end-to-end idea how to go from the original formula phi that we wanted to enforce into all the way down to the corresponding optimization problem. And so, of course, once you solve this inner optimization problem, you can just plug in that value of Z that you get, as we discussed, into the original formula, into the translation of the original formula, trying to find, it will give you essentially the maximal violation of that formula. And then with the outer minimization problem, you'll be trying to minimize that. Okay, so hopefully this gives you an end-to-end picture via an example of what happens here. So let me just paste this. All right. So in summary, what we looked at in this lecture is how do you combine deep learning and logical constraints. In particular, we looked at two kinds of directions. One was in querying the neural network, seeing the neural network as a database and posing queries to that neural network, right? And the second one was enforcing background priors. And in both of these cases, we had to define a logic using which we can express our queries or express our declarative knowledge or knowledge about the world, or the properties we want to enforce, right? And that logic then we could have, of course, a high-level language like we saw with the class keyword that makes it just easier to write queries, which gets compiled into the logic. The logic itself has some connectives there, for instance, implication, which we rewrite also in just the more basic connectives. And now to deal with the logic, to bridge these two worlds of logical reasoning and formal reasoning with the differentiable space, we saw how to rewrite the logical formulas into a loss function with a specific mathematical property that if the logical formula is satisfiable, then that satisfying assignment makes the resulting loss 0. And if the loss is 0 at a given point, then that point is a satisfying assignment of the original formula, okay? And so we looked at that translation, and this is one particular translation, this logic to loss that we're showing here on the right. Just to recap, there could be other translations from logic to loss which also satisfy the theorem, and you're welcome to explore and think about those. Once we have this translation, we can use it both for querying and for enforcing background priors, okay? And for enforcing background priors, we expectedly had to define an optimization problem which tries to enforce the formula into the model, tries to find parameters theta where the formula holds. And this was, to make it more convenient for optimization, this was rewritten as trying to find counterexamples, right, violation to the original formula, which maximize this violation. And once it's rewritten in this way, we can then translate the logical formula into a loss, and then just use optimization in order to find these violating counterexamples, right? So this is what we get. This is this connection between the logic and the resulting optimization problem. Okay, and this optimization problem that we looked at in that setting essentially can be thought of as generalized adversarial training. So having formulas phi that are not just about robustness, but about some other beliefs that you may want to enforce. Okay, and we saw some examples of some formulas that you may want to enforce in both the supervised setting and in the semi-supervised setting, and it turns out that they're actually helping not just in enforcing the priors, but even helping in improving the natural accuracy of the resulting neural network, which is quite interesting and promising in potentially in reducing the amount of label data. Okay, and finally, in order to solve this optimization problem, we need to be wary of the fact that we may get constraints which are hard to optimize with gradient-based methods, and thus we are expectedly may have to take them out of the optimization. And when we do projected gradient descent for optimizing this constrained optimization problem, just take them out and then project on this ranges, these convex sets that the variables that are difficult to optimize with standard gradient descent can range over. This is the same high-level idea that we already saw earlier when we discussed adversarial training and adversarial example generation. Okay, so I hope that you enjoyed the lecture, and see you next time.